Good morning, everyone. I'm Sherry Ann Sakriyas, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. Today, I'll be discussing on the topic MEMS and microsystems, which comes under the elective MEMS for S7EC students. The contents of this presentation are as follows. We will start with an introduction to what is MEMS, then we will discuss on the components and characteristics of MEMS, then we will look at the multidisciplinary nature of microsystems engineering, and then we will discuss on what are microsensors and the different types of microsensors such as a pressure sensor, biosensor, chemical sensor, acoustic wave sensor, optical sensor, and the thermal sensor. The reference textbooks are Foundation of MEMS by Chang Liu and MEMS and Microsystem Design and Manufacture by Tyran Su. Now, what is MEMS? MEMS stands for Micro Electromechanical Systems. It can be defined as any engineering system that performs electrical and mechanical functions, and the component has a size of the order of micrometers. So this term MEMS was originated in the US, and in other places such as in Europe it is referred to as the microsystem technology, whereas in Japan it is known as micromachining. So in a MEMS device you have electronic components as well as micromechanical components. The electronic components are fabricated using the computer chip or IC technology, whereas the micromechanical components are fabricated using micromachining processes. Micromachining refers to techniques that are used in the fabrication of MEMS, which are of two types. You have bulk micromachining as well as surface micromachining. So MEMS can be defined as any engineering system that has sensors, actuators, along with signal processing circuits all integrated on a single wafer. Now we look at the components of MEMS. So you have an input signal which is given to a microsensor. The microsensor generally converts a non-electrical signal into an electrical signal. So the sensor is a device that is used to detect or monitor some kind of physical or chemical phenomenon. And then this signal is given to a microprocessor or controller, which performs a set of mathematical or logical operations on the input signal. At the output of the microprocessor or controller, you have a control signal given to the micro actuator. The micro actuator generally converts an electrical signal into a non-electrical signal. So the function of the actuator is used, it is a device that is used to produce some kind of mechanical motion such as force or torque. Now the main characteristics of MEMS are as follows. The first one is miniaturization. The typical size of MEMS devices ranges from 1 micrometers to 1 millimeters. So the advantage is that smaller systems tend to move more quickly than larger systems due to lower inertia of mass. Similarly, greater precision can be achieved. Smaller devices also face fewer problems of thermal distortion as well as vibration. Okay, so smaller the size, it makes it more suitable for applications such as biomedicine, aerospace, etc. Now, another important characteristic is microelectronics integration. That is the ability to integrate mechanical sensors, actuators along with your electronic processors and controllers at a single wafer level is one of the unique characteristics of MEMS. This is also known as monolithic integration. The third characteristic is parallel fabrication. So many of these micro devices, they can be integrated to perform a single task. So multiple copies of identical die can be made on a single wafer. So this results in batch production, which in turn reduces the unit cost. So this figure over here just shows the size comparison of a MEMS chip. So here you can see a MEMS silicon motor together with the strand of a human hair. So this is of the order of 50 micrometers. Similarly, the second figure over here shows the gears of a micro engine, and you can see the legs of a spider standing on the gears. Okay, so that shows the size of the gears is of the order of 20 micrometers. So it's really very small. Now we will look at the multidisciplinary nature of microsystems engineering. So there are several science and engineering disciplines involved in the design and manufacture of MEMS devices. So like for example, you have electrochemistry, which is used in electrolysis and the design of chemical sensors. Then you have electrohydrodynamics, which is the driving mechanism of fluid flow in microchannels. Similarly, you have molecular biology and biochemistry that is used in the design and manufacture of biosensors. Then you have quantum physics, which is used to model certain physical behavior of materials and substances. Then you have scaling laws, which is used for scaling down the physical quantities in order to create the MEMS devices. And you also have material science. Similarly, you have 5 main engineering disciplines, such as mechanical engineering, which is used for the design of the microstructures and packaging. Then you have electrical engineering, which involves the electric power supply, the control and signal processing circuits. Then you have chemical engineering, which is used in microfabrication and manufacturing. Then you have materials engineering, which is involved in the design and selection of materials for the development of sensors. And then you have industrial engineering, which is related to the production as well as the assembly of the microsystems. Now we will look at the working principle of different types of microsensors. So what is a microsensor? A microsensor is basically a device that is used to detect or monitor some kind of physical or chemical phenomenon, or it is a device that converts one form of energy into another. So microsensors basically fall into two main categories: the physical sensor and the chemical or biological sensor. So physical sensors are used to measure physical parameters such as force, acceleration, pressure, temperature, flow rate, or acoustic vibration. Similarly, chemical or biological sensors are used to detect some chemical or biological parameters such as the concentration of chemicals, pH, the binding strength of biological molecules, and so on. So this figure shows the block schematic of a microsensor. You have an input signal given to a microsensing element that is given to a transduction unit, which is responsible for converting one form of energy to the other, and you get the output signal. Okay, so the main advantages of microsensors is that it is very sensitive. You require a minimum amount of the sample substance, and it can be produced in batches. So the first type of microsensor that we will be discussing is a pressure sensor. So the figure on the left shows a micro pressure sensor after packaging. So you can see the size of this micro pressure sensor is very small compared to the size of a coin. And the figure on the right shows the various elements of this micro pressure sensor. Okay, so the input to the pressure sensor is a pressure from some source. Okay, and the sensing element is a silicon diaphragm which is etched out of a silicon substrate. Okay, and there is a silicon gel that is used to separate the diaphragm from the incoming fluid. Okay, and the aim of the pressure sensor is it has to sense or measure the pressure of the incoming fluid. Okay, so now the silicon diaphragm is connected to piezo resistors. Okay, and based on the applied pressure, the silicon diaphragm will deflect. Okay, the deflection of the silicon diaphragm is converted to a corresponding change in electrical resistance by the piezoresistor. The piezoresistor is in turn connected to a Wheatstone's bridge, which converts the change in resistance to a change in voltage. So the output of this pressure sensor is a voltage change corresponding to the input pressure. The working of the pressure sensor is explained here. So this kind of a disposable pressure sensor can be used to monitor the blood pressure by connecting to the intravenous line. So a gel is used to separate the saline solution from the sensing element. The sensing element is the silicon diaphragm. Okay, and you have a piezo-resistive layer which is applied on the surface of the diaphragm. The deflection of the diaphragm will correspond to the pressure of the saline solution that enters the passage, and that deflection is converted to a corresponding change in voltage by using a piezoresistor as well as a Wheatstone's bridge. The next type of sensor is a biomedical sensor. A biomedical sensor is used to measure the biological substances, as well as it can be used for medical diagnosis, drug discovery and delivery. So the main advantage of a miniature biomedical sensor is that you can do the analysis of the sample in a very quick and accurate manner, and you require only a very minimum amount of sample. So this figure shows a biosensor that is used to measure the glucose concentration of a patient. So here what happens is that a small sample of blood is introduced to the sensor with a polyvinyl alcohol solution, and there are two electrodes which are present in the sensor. You have a platinum electrode and a reference electrode made of Ag or AgCl, and what will happen is that there will be a chemical reaction between the glucose which is present in the blood sample and the oxygen in the polyvinyl alcohol solution. So as a byproduct, what will happen is H2O2 will be produced. Okay, and this H2O2 produced will get electrolyzed by applying a potential to the platinum electrode. Okay, so that will result in positive hydrogen ions getting accumulated at this platinum electrode. Okay, so the amount of glucose concentration in the blood sample can be measured by simply measuring the current flow between the two electrodes. So the working principle is explained here. The glucose present in the patient's blood sample will react with the oxygen in the polyvinyl alcohol solution and produce H2O2. This hydrogen in the H2O2 will migrate towards the platinum electrode by the process of electrolysis, and it will build up layers at that electrode. Because of that, there will be a difference of potential between the two electrodes, and that will relate to the amount of glucose present in the blood sample. The next type of sensor is a chemical sensor. So chemical sensors are used to sense the presence of some particular chemical compound. So we know that most materials are sensitive to chemical attacks. For example, if you consider metals, when exposed to air, it has a tendency to get oxidized. That is, a significant oxide layer builds up, and that oxide layer can change the material properties of the sample. So a chemical sensor works on the principle of chemical reactions between the sample and the sensing element. For example, a metal. So here signal transduction refers to the change of physical properties of the sensing material after a specific type of chemical reaction. So this figure shows the working principle of chemical sensors. So you have an input measurand gas which undergoes a chemical reaction with the sensing element, which can be metal inserts or metal electrodes. And in order to measure the presence of a chemical compound in the input sample, that is done by measuring the change of resistance or the change of capacitance after the chemical reaction. So there are different types of chemical sensors. For example, a chemi-resistor sensor. So in a chemi-resistor sensor, you have organic polymers are used along with the embedded metal inserts. So when this polymer is being exposed to the input sample or the measurand gas, what happens is that there is a change in the electric conductivity of the metal. Okay, so for example, you can use a polymer such as phthalocyanin, can be used along with metal inserts such as copper in order to sense the presence of ammonia and nitrogen dioxide gases. The second type of chemical sensor is a chemi-capacitor sensor. So here there is a capacitor structure. So you have two metal electrodes separated by a dielectric material, and here polymers are used as the dielectric material, and by exposing these polymers to the input sample or the measurand gas, the dielectric constant of the material changes. So as the dielectric constant changes, we know that capacitance C will also change. Okay, so by measuring the change in capacitance, you can measure the gas. So here for example, a polymer such as polyphenyl acetylene, PPA, this is being used in order to measure gas species such as carbon monoxide, carbon dioxide, nitrogen, and so on. Okay, so the third type of sensor is a chemi-mechanical sensor. So here the principle is certain polymers have the ability to change their shape when exposed to chemicals. Okay, so here in order to determine the presence of a chemical, you have to measure what is the change in the dimension of the sensing material. Okay, so by measuring this change in dimension of the sensing material, you can determine what is the presence of the chemical. So for example is a moisture sensor, which is implemented using pyroline PI2722. The last type of chemical sensor is a metal oxide gas sensor. So certain semiconducting materials such as SnO2, okay, when it is exposed to measurand gases, its electrical resistance changes. So by measuring this change in electrical resistance, you can actually measure the chemical composition. So here, in order to improve the reactivity between SnO2 and the measurand gas, you can apply heat. So the next type of sensor is an acoustic wave sensor. So an acoustic wave sensor, what happens is that acoustic waves are generated by converting mechanical energy to electrical energy. So this can be done by two principal mechanisms. One is the piezoelectric effect and the magnetostrictive effect. So the most popular method is the piezoelectric effect. Piezoelectric effect basically states that certain materials have a tendency to deform with the application of an electric voltage. The reverse is also valid. That is, when an electric voltage is applied across certain crystals, the structure deforms. So the applications of your acoustic wave sensor is that it is used to measure the chemical composition in a gas. It can be used to sense the torque or tire pressure. Similarly, it can also be used to actuate the fluid flow or monitor the fluid flow in microfluidics. So this figure shows an acoustic wave sensor. It consists of two sets of interdigital transducers that are placed on a piezoelectric thick film which is attached to a substrate. So the input IDT is energized using an AC source. So this will close and open the finger electrodes, which will result in a surface deformation or stress. This stress is being transmitted through the piezoelectric material, and it will cause a change of the finger electrodes in the output IDT that will result in an output signal. So here the acoustic wave that is generated, if there is any change in the material properties or geometry, it will alter the input output between the input IDT and the output IDT. So that is what is explained over here. The next type of sensor is the optical sensor. The optical sensor, as the name suggests, it is used to detect the intensity of light that is falling on the sensor. So it works on the principle of energy conversion between the photons which are present in the incident beam of light and the electrons in the sensing material. So the materials which are used in creating optical sensors should have a high quantum efficiency. So quantum efficiency is the ability of a material to generate electron hole pairs from the input photons. So the commonly used materials are silicon, gallium arsenide, and so on. So gallium arsenide is a material which has higher quantum efficiency. There are four different types of optical sensors: photovoltaic device, photoconductive device, a photodiode, and a phototransistor. So this figure shows the different types of optical sensors. The first one is a photovoltaic junction. So it consists of two layers of semiconducting materials forming a junction. So based on the intensity of light falling on the junction, it produces a corresponding electric voltage. And the second one is a photoconductive device. So the conductivity of the material changes in response to the intensity of light that is falling on it. And the next type of sensor is a photodiode, which consists of a PN junction which is operated in reverse bias, and here you have a phototransistor which is a three-terminal device. So both the photodiode and the phototransistor, what it does is it converts the incoming light energy and you're converting it into a corresponding electrical energy. The next type of sensor is a thermal sensor. Thermal sensors are used to measure thermal properties such as temperature or heat of an environment. So the commonly used thermal sensors are thermal bimorph sensor, thermocouples, and thermal resistive sensors. In a thermal bimorph sensor, there is a bimorph element, which is a beam that is made of two different materials joined along a particular longitudinal axis. And here the temperature variation can be measured by looking at the displacement of the mechanical beams. The second type of thermal sensor is a thermocouple. So thermocouples, they work on the principle that an electromotive force is generated whenever the junction of two similar materials is getting heated. The third type of thermal sensor is a thermal resistive sensor, in which the temperature variation is being sensed by measuring the change in the resistance of the material. So we will be focusing mainly on the thermocouple. So the thermocouple is basically when you have two wires of different materials which are joined at one point, this constitutes a thermocouple. Okay, and the main function of the thermocouple is that it is used to measure the temperature difference between the joined sensing junction and the reference junction. Okay, so here generally thermocouples are being made of materials such as chromyl, constantan, chromyl, alumyl, and so on. Okay, so when you apply a temperature difference or when you heat the joined junction, what happens is that an open circuit voltage gets generated, and this voltage which is generated at the reference junction is proportional to the temperature difference. That is, here delta V is given by alpha A minus alpha B into delta T, where alpha A and alpha B are the Seebeck coefficients of each of these two materials A and B. Okay, so the Seebeck coefficient is defined as the ratio of the change in voltage to the change in temperature. Okay, so the disadvantage of a thermocouple is that the output of the thermocouple is going to decrease as the size of the wire and beads reduce. So in order to overcome the drawback of the thermocouple, we use thermopiles. So this figure shows a thermopile. The thermopile is made by connecting a series of thermocouples in parallel. So here you can see that there are three thermocouple pairs connected in parallel. So you have the sensing junctions here, and this is the reference junction. So the voltage that is generated at the reference junction will be proportional to the temperature difference between the two junctions. So here in this case, delta V is equal to 3 into alpha A minus alpha B into delta T, where 3 refers to the number of thermocouples that are used in creating the thermopile. Alpha A minus alpha B is the difference in the Seebeck coefficients of the two materials used to form the thermocouple, and delta T refers to the temperature difference. So to conclude with, in this presentation, we started off with an introduction to MEMS, then we discussed on the main characteristics and the core elements of MEMS. We also looked into the working principle of various microsensors such as the pressure sensor, the biosensor, chemical sensor, acoustic, optical, as well as thermal sensors. Thank you.